Good afternoon, students. We will continue our discussion on low power VLSI design from last class onwards. So, last day we discussed about different classification of digital VLSI technology. So, if you see the progress, so we have NMOS logic, then we have CMOS logic. So, these two falls in the category of static CMOS circuit or static design, and this is dynamic logic. So, earlier days, so here if you see the NMOS logic with resistive load, NMOS logic with depletion mode load and NMOS logic with enhancement mode load. So, we have options of three type of load. These are active load and this is passive load. So, if we see a circuit, so suppose this is your circuit resistive, so this is your NMOS and this is your load. Okay. So, this DI is your input digital, as we are considering this for digital circuit. So, I have taken DI as digital input. So, suppose your input is 0, what will be your output? 0 means this MOS is off. So, whatever the, so through this path no current flows, and suppose this is a capacitive loading. Okay. So, no current flows, so this output will go to logic 1, right. And if you are having high input, like say this is equal to VDD, so this MOSFET will turn on and a current of ID, where ID is equal to half mu n COX W by L VGS minus VTH whole square, that much current will flow. So, as input is maximum possible, right, VDD, this is your maximum possible input. So, you think that this is strongly on. Okay. So, strongly on means very large current will flow. So, what will be your output now? V0 is equal to, previous case no current flowing, so it was VDD. Now, VDD minus IR drop, right. So, VDD, so I current flows through this, so what is the drop? ID into RD. So, rest of the voltage will be available at your output. So, roughly speaking, suppose if this is large, if input is close to VDD logic 1, so this current will be large, this is designed, because this is designed for digital applications. So, this will be, these values of R will be chosen such a way, so that this IDRD will be close to VDD. So, that you get a, this 0 is not exactly 0, this is logic 0. Okay. This value may not be 0, but the level will be considered as a 0. So, this is logic actually, this is not a actual value, it is not that, it may not be 0, maybe 0.2, 0.3. Okay. So, that we have to solve the actual circuit and check, but this is the idea, right. So, in this case, this is your driver, this NMOS is your main transistor, which is defining your logic, output logic. And if your input, you see this is behaving like which logic? Which gate? NOT gate. So, this is your inverter or NOT gate. So, this is known as the resistive load NMOS logic. Okay. Now, as we moved into VLSI, so this resistance is replaced by some active device. Okay. So, why to do that? Because this resistance is a passive element and it will take more area, right, and some resistive loss is there. So, what we can do, we can just replace this . So, this resistance can be replaced by a MOS. Okay. This MOS will have some resistance, right. I will give some bias voltage. Okay. So, this can this PMOS MP can be biased in active region. Okay. If it is biased in an active region, what will happen? In this zone, right. So, this is your I, this is your VDS, right. So, if you take a invert of that, you get this slope. If you take a del V by del I, this change is del V, this change is del V and this change is del I. So, this slope is actually transconductance del I by del V. If you take inverse of that, you will get a del V by del I and you will get it as R on. R on means resistance at the linear region, right. So, you see this is more or less, if you consider this approximately a chunk, it will be more or less a constant resistance, right. As a through, it is a variable resistance, this slope is varying, right. But if you consider it for a small portion of it, you can approximate it as a fixed R on. Okay. So, this can replace this resistance, right. So, this is called active load. This was a passive load. I just replace this, input is given to this. So, this still remain my driver, but this is a active transistor, but this voltage is not my input voltage, this voltage is a fixed voltage, DC voltage. So, this will be behaving like a load, clear. So, this is known as the active load, clear. So, this is just replace of this resistance. Okay. In this domain, this is transistor is in which field, which region? Saturation region. Can you tell me saturation and linear, where the resistance is more? In saturation resistance is more, because ideally del I is 0. So, ideally it is infinite, right. So, if you want to implement a bigger resistance, we can think of this. So, current source load. Okay. So, in this case your voltage is changing, but current is fixed now. So, if I model this transistor in saturation mode, this can behave like a fixed current source of value I. So, this is called, you see the same thing, just how the circuit is varying, the definition is getting varied. This is, this MP is in linear mode, R on. Now, if I want to use this in the I can use this VB, so that this MP is in saturation, then this will be just like this circuit, is not it? This, if it is in saturation, this will provide, always provide a constant current. So, this is known as the current source load, constant current source load. Okay. So, same structure is same, only what is changing, this voltage is changing. So, that in this case it is in saturation, in this case it is in linear, clear. So, this constant current source generally we will see this its application in analog circuit, not in digital circuit. In digital circuit generally we see in this linear scale can be sufficient. Another modification we can do, we can add this together. Now, do you know this circuit? This becomes your CMOS logic. Okay. Now, what is happening? When this is a driver, this is a load. When this is a driver, this is a load. They exchange their operation. What is the meaning? Meaning is, for certain voltage this will be on, na? Okay. Then this other will behave like the load, just like the resistive load we discussed. Okay. So, this is called the, so this is actually is discussed here. NMOS logic, 3 variations are there, one is resistive load, one is, this is structure is different, one is enhancement mode. Generally our MOS are enhancement mode, right. We need to enhance our VTH so that it is working. We need to enhance a VGS so that it goes above VTH and we get a current. So, normal MOS are enhancement mode MOS. Depletion mode is there already a channel is depleted, so that even at 0 voltage you will get a current. So, if you want to turn it on, you have to give a negative voltage, that is depletion mode. Okay. But this enhancement mode we can have two type of operation, the load could be in linear region or in saturation region. CMOS logic is our classical CMOS logic that we just drawn, or we can have a transmission gate or CVSL logic. This logic, different type of logic we will discuss later. So, now if I ask you what is the difference between a static logic and a dynamic logic, why it is known as static and why it is known as dynamic, any idea? Have you studied this, any of this, domino logic, nodal logic, studied? So, why it is known as dynamic and why this is known as static, how the structure is different? Capacitance, load at output, then what will happen? Suppose this is your logic. Now, see this capacitor will be always there, the load is capacitive, because a gate may be a driving another gate, right. So, what it will see? It will see a capacitance only, because it is driving the gate of something, right, gate of the transistor. This is connected to the gate, right, and gate is nothing but a oxide cap, COX. So, your capacitance will be COX into W into L and its modifications, right. So, any digital logic is actually driving a, you can think of that it is driving some capacitance. So, load is always capacitance, be it static, be it dynamic. Now, the difference is this output, this is my output, this node is my output, right. So, this will be either 0 or 1. These two are the possibility, right. Digital circuit are having binary logic. Binary logic have two values only, 0 and 1. So, you see when it is 0, this cap is connected to the ground through which? Through this NMOS. So, it is strongly connected to the ground. For example, suppose I gave 1 at the input and I kept it for indefinitely. Okay. So, what is the meaning? This 0, this capacitor, this NMOS will be turned on, and so this node will be virtually shorted to ground. So, this capacitor will be discharged to ground through this NMOS. For example, then I change this 1 to 0 for a long time. So, what is happening? This PMOS turns on. So, this VDD will charge this cap to 1. Now, will this voltage discharge? The moment this capacitor is discharged, again this current path will charge it on. So, you see from the VDD and ground a strong connection always exists. So, that is why it is known as the static logic. Okay. But same will not be there in the dynamic. If I keep a dynamic logic and keep it for whole day, it will leak out. Suppose I stored a 1. So, what happens in dynamic logic? Something like that. There will be a switch and a cap, and this switch will be kept open. Suppose I charge this up to 1 and keep this switch open. Now, it is the responsibility of the cap to hold the charge, hold the 1. So, it will hold this 1 for some time. Then this capacitance is a leaky capacitance. There will be so many parasitic currents, right. Through the parasitic connections, this current will flow and this capacitor voltage will be discharged. Capacitor will be discharged, and so this logic it was holding, it will try to fall. So, unless I refresh it again, it can't hold for long. This is the difference, primary difference between the static and dynamic logic. Both the cases capacitor is there, but the connections, the style is different. In case of static, it is always connected to the VDD and ground through some strong connection. Okay. But in case of dynamic, it is not connected to the, there will be high impedance state, right. The any of the MOS will go off and the capacitor will be discharged from the VDD or ground side. Okay. So, we will discuss this later, but roughly you all know what is this. So, we will check that which is more power efficient. Later we will discuss all of this and we will try to see which is more suitable for low power applications. Okay. So, this design flow we already discussed. We have to check the logic functionality and we have to maintain certain target, for example, operating speed, what is our area, what is our power consumption and what is our noise margin. So, this will be used for used to compare how your design is performing as compared to a suitable benchmark or previous model. Okay. And in each phase you have to verify verifications and iteration may be needed. If its performance is not satisfied, you need iterations. So, this is after layout. If you consider the parasitic extracted model, then you will be seeing that in ideal case your input and output are mostly ideal. Okay. But when you consider the real parasitic model, you will be seeing that is sloping down. Okay. If you have a bigger load, if you keep on increasing this capacitive load, then what will happen? Ideally, you should get a sharp edge, right. But as you keep on increasing this C value, what will happen? It will be difficult to drive this node, isn't it? Capacitance follow the exponential nature, right. So, if this C value keeps on increasing, your RC time constant is also increased, right. So, it will take more time to charge it up, right. So, it will exponential, it will be delayed, or you can say that. So, if you have an ideal response, it will be just a square pulse, okay. And as you keep on increasing your capacitance, or if you do the ideal schematic simulation and then you do a layout and do the post schematic simulations, then you will be seeing that this slewing you will be seeing. Okay. That means, maybe after layout you will be seeing that suppose you have designed this inverter with minimum size, it may happen. Okay. So, this minimum size may not be sufficient to drive the load. Okay. For digital design, what is your length? What is your suitable length you choose? We have a PMOS, right? We have an NMOS and we have an PMOS. Suppose this is W by L. What should be the size of the PMOS? Roughly 2.5 to 3 times, right? So, say 2.5 into W by L. You know why? I hope you know. Because mu n is roughly 2.5 to 3 times of mu p. So, the NMOS is doing which portion? Which NMOS is pulling the output to the 0. So, if you make it W by L, PMOS also W by L, you will be seeing that it is going to 0 sharply, but it is taking time to go to 1. Why? Because current in NMOS is more, but current in PMOS is less if you keep the same size, because mu p is much less value of mu n. Clear? To compensate that my rise and fall, they are of same time delay, symmetric. What we do? We generally make this W bigger, 2.5 to 3 times. Now, okay, W if chosen, then this W you will know that at least it will be 2.5 times. Now, my question is, what L value you should choose for digital logic design? Suppose your technology is fixed, say 90 nanometer. So, minimum size you will be taken, right. So, this L it should be always minimum. Clear? So, this L is the lowest your technology is offering you. If it is a 180 nanometer, you choose 180 nanometer. For digital design, L lowest. W could be bigger depending on my how much load it is driving. Clear? Suppose this is your inverter and it is driving another 5 inverter, and you have designed this with a minimum W and minimum L. So, it may not be sufficient to drive all these 5. Okay. So, generally we have a library, we choose from this. So, in the library we have different design, different inverters. One is for low power, one is for high speed. So, low power is generally for minimum design, but when you are connecting it to what is this known as fan out, right. If your fan out is more, you may be careful about the sizing, because otherwise what will happen, this kind of scenario will happen and it may not be able to drive. Okay. But L should be always minimum. Now, my question is, why L is minimum? Okay. One is increasing the current value, take a next. R on is L by W to reduce the switch resistance, that is another reason. Next, area. In digital circuit, your job is to have more number of transistor, right. So, your area, to increase the area, if we have the minimum area, to reduce the area actually we use minimum L, and this is another reason, R on. Okay. See, in digital your transistor is operating just like what? Just switch. I am having a switch here connected to VDD, or this is connected to ground. So, this switch is made up of the PMOS. If this is on, my output is connected to the VDD. If this is made up of NMOS. If this is on, my output is connected to the ground, right. So, my transistor is just behaving like a switch, nothing else. So, if it is a switch, what is the model of a switch? Switch will have some on resistance, right. So, ideally this switch should have 0 resistance, clear. Switch, the job of a switch is to connect, no drop should be there. So, we just discussed in which mode our resistance is minimum, saturation or linear? Linear. So, that is why in digital logic you will be seeing that my transistor is operating in cutoff, when it is off it is in cutoff mode, when it is on it is in linear mode. But in analog you want to make a amplifier, you want to make a current source. So, transistor should be biased in saturation domain. You are studying analog in this semester, right. So, you will be saying they will be discussing only in saturation. In digital circuit we will be saying only in linear. Okay. So, this is the reason. So, we want our transistor to be in low resistance, and what is resistance? R on proportional to L by W. So, if we keep L bigger, unnecessarily we will be making area bigger and resistance bigger, that is not wanted. So, we choose, make it simple, digital circuit L is minimum, but in analog circuit you will be seeing that you have to choose the values of L also. Okay. That is why it is difficult there to choose the values, but for digital circuit it is easy. So, we have 3 mode: cutoff, linear and saturation. In digital we will be just working in cutoff and linear, and that if you draw the VTC of an transistor, VTC of an inverter, that linear slope, that is all the analog designer will exploit that linearity. Y is equal to mx, that straight line is a y is equal to mx equation, so they will use that portion. But digital designer they will use flat zone, saturated zone, op amp are there. So, this is how the evolution happened. Okay. So, as we progressed year wise, so we can see the how the number of transistor count increased. Okay. So, this is a processor, this is the source is Intel, and as the number of transistors are increasing throughout the year following the Moore's law. Okay. So, what will happen? Okay. So, it will follow the Moore's law for this is a for microprocessor it is shown. So, transistor count just doubles every 2 years. So, 1.5 to 2 years it will, so it just doubles 2x growth. Okay. Now, this will in this growth what will happen that our power consumption or power density that will also go up. Okay. So, this growth, this is happening because our this L is sinking, right. The transistor length technology node that we tell, that is sinking in throughout this year, this technology is evolving, right. So, this length is shrinking. So, on the same area you can stack more number of transistor. Okay. And also the interconnect, that is also improved, the parasitic capacitance that is improved. So, the result is your frequency of operation is increased. Okay. So, our frequency of operation is also roughly doubles every year, every 2 years. Now comes the problem. Okay. So, what we are seeing that exponentially our power is getting increased. Now, why this power dissipation is becoming a major problem? Because this power dissipation, large power dissipations, it will ask some power density. This power dissipations, if you dissipate more power, you will generate more heat, right. So, for semiconductor ICs, your area is generally in micrometer square, right. Area is very small. So, the generated heat per area, unit area, if you check that unit, this could be equivalent to a rocket nozzle temperature. Clear? The heat dissipated, if you check the heat density, okay, because our area is so small, the heat density is equivalent to very large. Clear? So, as this heat that is generated, that is sufficient to destroy your IC. What will happen? The metal interconnect that may melt, creating a short or open. Okay. Your transistor could be destroyed, oxide could be broken. So many things can happen. Performance could be degraded, that we discussed last day, that your operation specification, technological specification depends on temperature. So, they will vary. So, your performance will vary. Okay. Apart from that, apart from performance variations or degradation, another risk is failure of the IC because of the heat density. So, this becomes so critical that it is you need to keep the power at some boundary, or you have to make some arrangement for heat dissipations, cooling fan or cooling liquid, something should be there. Okay, so these are some applications. In this is also already we discussed RF applications, power management, analog signal, digital circuit, including the MCU and other digital logic. So, these are challenges in the digital VLSI designs. So, few are macroscopic, few are microscopic. So, microscopic is this maintaining speed, interconnect, reducing the noise, crosstalk, maintaining the reliability, okay, maintaining the power dissipations, clock distributions, all of these are challenges. Few important things are time to market, okay, parasitics, millions of gates you have to consider, power, reliability, and macroscopic issues are, these are macroscopic issues, the window from the product decision to product development, this window. Okay. So, reusability of the IP, if you can, the abstraction that we discussed last day, that from high level onwards you have to model it and check that if this architecture is suitable or not. So, high level abstraction and cross verifications or simulations. If you have any, suppose you are moving from one design to second version of the design, if you, is it possible to use some of the previous design in your technology, newer technology. Suppose your previous design was in 180 nanometer and you are moving to 22 nanometer or 40 nanometer. So, can you use the previous IP or can you port it to the new technology? Is it easily portable? So, these all of these issues will define your how quickly you could make the next version. If the previous IP is portable, means it is technology independent, then your job is little bit easier, right. You can previous IP you can directly use or with little modification you can use. So, all of these you have on the large scale or on a broader point of view, you have several challenges, and on the smaller level, because you are in the microscopic level, right. So, both cases you have several challenges. Okay. So, in this case, microscopic cases, our problem because of the reduced size, and in this macroscopic scape our problem is for because of large number of transistors. Now, these are the challenges that we have to struggle with. that technology shrinks by 0.7 times per generation, and with every generation it can integrate 2 times more. But cost of the function, this decreases also by 2x. These are few design abstraction from the system level to the device level. And if we talk about the full cycle, complete signal cycle, in our real life signal, our signal is in analog, right, and we are doing the processing in digital, and the end user is also, as we want to, as we for human, it is we are adaptable to the analog signals, right. Digital signals are more suitable for the machines. So, again we need to convert it to analog. So, for any signal processing chain, two important conversion is there, one is analog to digital and another is digital to analog conversion. So, ADC and DAC are two another important block for this full signal processing chain. Now, I hope you all know what is the difference between analog signal and digital signal. So, analog signal are continuous in nature, right. So, if I think of say 0 to 0.5, I can have infinite levels. The difference between analog signal and digital signal is that in between this any two voltage, you break it, then again in between them I can have infinite signals. Its storage is huge, calculation is continuous. But in case of digital, I have only two level, 0 voltage level and VDD voltage level. This data point, even if you skip, it does not matter, you will just connect this, right. But in this case, you cannot skip this data point, this may have its meaning. So, for any analog signal, this voltage mode is continuous, time mode could be discrete. Now, when you want to convert a analog signal to a digital signal, first step is to discretize. See, I am having this signal, this is moving from 0 to say 1 volt. Now, continuously each voltage I cannot copy. Suppose 0 volt I will sample and I will convert it to equivalent digital. For this conversion I need some time, and by this time my voltage will be changed to some other level, is not it. So, I have to whenever I am converting from analog to digital, I have to accept that I will lose some accuracy, is not it. Whenever I am converting from analog to digital, some information are lost. This is known as the quantization noise or quantization error, because I am converting a continuous signal to a stepwise discrete signal. So, this level I will sample. So, this is my first step, step 1, this is my step 2, and I will take some time to convert it to equivalent digital value, and by that time my input is moved. Okay. So, this is known as the sampling frequency. This was my signal frequency. Now, I need to sample it. Okay. This sampling frequency generally happens with clock frequency. Have you heard about Shannon's sampling theorem? Can you recall that? We can reconstruct a signal if we sample it at least twice the signal frequency, right. Suppose this is your signal, this is a sine wave, and suppose you are sampling just one data. Can you reconstruct the sine wave? No. But if you at least get few data, then it will more or less you can reconstruct the original signal, right. So, Shannon's theorem tells that your sampling frequency should be at least twice the maximum frequency component, that is known as the Nyquist signal, right. So, this is the first step in this conversion. First is sampling, next is quantization, and then conversion. Okay. So, not getting into details, but please understand that there are ADC and DAC involved for any kind of signal processing. You think of any signal processing, real life signal processing, these two, or in this signal chain you need to have a ADC and DAC, and in between your digital processor is there. But if it is a real life applications, be it in any sensor, suppose temperature sensor or any sensor, your signals has to be analog, and at the end also it has to be converted back to analog. Okay. Few examples are data converters in your audio codec, okay, audio amplifiers, and different architectures. So, that we discussed that about the selection of architecture. Okay. You need to choose that what is your application, what is your specifications, in which frequency you will be operating, and for that frequency which application is, which architecture is more suitable. For example, this flash, you may have heard about flash ADC or ramping ADC. No, this is flash. Flash is having very high speed, this is comparator based ADC, right, but its problem is it takes consume very high power, and also its resolution is very low. This is resolution, how many bits. Okay. If your resolution is large, you can go for sigma delta or ramp type. If your resolution is moderate, say 10 to 12 bit, and your frequency is also moderate, you can go for pipeline ADC. So, that way we have to choose our architecture. Similarly, if your application is low frequency and moderate or to high resolution, you can go for SAR applications, SAR, successive approximation resistive type ADC for low power applications. So, that you need to check by doing the literature survey. Okay. These are few application of the DACs, digital motor control, computer printers, sound equipments, function generator, oscilloscope, digital audio. Okay. So, if we look around, these are several applications of VLSI that is very closely integrated in our day to day lives, starting from TV, laptop, PCs, smartphone, car appliances, okay, server. So, all of this, so this is everywhere. Okay. So, in your future you could be anywhere, any of these applications, starting from medical applications, automotive, aerospace, defense, okay, design automations, wireless. So, this is applications oriented, and if you look from the design perspective, you could have front end designer or back end designer or device engineer, okay, or even for fabrication also, fabrication procedure, fabrications expert. So, in VLSI we have several job opportunities, scope of the opportunities. All right. So, let us stop here today, and in next class we will start with a new topic. In next class we will start with device structure and fabrication procedure.